This video is about chapter 11, section 2, the peculiarities of the prop universe. In the last video, we have, just scroll up here, right. So in the last video, we've seen that the Lean has a whole hierarchy of universes. So starting from prop, and prop has type, and then type 1, type 2, type 3, and so on. So Lean has this whole hierarchy of universes, and while we can refer to them generically via sort, so prop is sort 0 and type is sort 1 and type 1 is sort 2 and so on, there is still a huge difference between prop and type. And this is not necessary. So we could theoretically have a Lean system where prop would be just like type. However, by making prop special, we gain a lot of nice features. And the special features that prop has in Lean are motivated by how I want to use it. So prop should be the universe of propositions. And the elements of prop are hence propositions, and their elements are hence proofs. And since in Lean we want to use classical logic, the one property that we want to have the important property that you should keep in mind when thinking about prop is that there are exactly two propositions. So every proposition that we have in Lean is either false or true. And this property motivates a lot of these nice features. So there are three major differences between prop and type in Lean. So the first difference is the universe of function types. So when we have types alpha and beta, what universe should alpha or beta live in? This is one way in which prop and type differ for good reason, as we will see. The second big difference is in the way Lean is able to unify proofs. This is called proof irrelevance. And the third big difference is in restriction of large elimination. So prop differs in the typing, in what type the error, like alpha error beta gets. It differs in the way Lean checks whether two types can be unified. And prop also differs in the way you can pattern match on propositions. Okay, so let us go through these differences one by one. Let us start with the universe of function types in Lean. So here in the demo file you have typed up these nice typing judgments. Important motivation to see why these should be different is to look at the ways at what function types can mean in Lean. So broadly speaking, function types in Lean represent three different concepts in mathematics or computer science. So one, as we've probably seen way too often, is function types can represent, well, functions. So like stuff that computes one natural number from another one, or more complicated function types that produce a list from a natural number or something. that maybe not even compute, but are just like some non-computable mappings. But there are like functions between data. Okay, so this is like the first way in which function types are used in Lean. So, well, we can also have dependent function types. What can I take here? Maybe a fixed size list. Okay, so but these are, both of them represent functions. So the second use of function types in Lean is in propositions. So here, function types represent implication via the Coriolis correspondence. So for example, we might have an implication between two propositions. So for example, 1 equals 2 implies 2 equals 3. So this is the second use of function types. And then we have a third use of function types, namely universal quantification. So for all statements, for example, for all n in NAT, for all m in NAT, n plus m equals m plus n. Okay, so this here is a proposition. And this here is just a dependent function type. However, it represents a for all statement. And so we need to keep this in mind when we want to define what should the universe of function types or generally dependent function types be. So for objects, like for functions between types that are in type, this should be in type with some suitable universe level and implications. So errors between propositions should be propositions because, well, implication should be a proposition. And for all statements, that is such function types where the right-hand side, the codomain, is a proposition, should also be a proposition, because we want for all statements to be propositions. Okay, this is what we want. And with these three examples in mind, let's take a look at the typing judgments. So in the first case, where we have a function type between types that are in type, the universe level is the maximum. Okay, this is the first case. And this also works for dependent types. There it is still the maximum. So Lean itself does not distinguish between non-dependent and dependent function types. Under the hood, an error is just a dependent function type where the x does not occur in the tau here. And the other two cases, implication and universal quantification for all statements, are subsumed by the same rule, which says that if the codomain of the function type is a proposition, then the whole function type is a proposition. Just that is exactly what we want. Note that for function types between types in type, the universe level is the maximum of the two universe levels, while for propositions, it does not depend at all on the domain of the function type. So here, when we type for all x in sigma tau of x, the type is always prop, no matter what universe the sigma lives in. And this independence, the resulting universe does not depend on the universe of sigma, is called impredicativity. While the other choice, of taking the maximum is called predicativity. And this is actually valid lean syntax. So we can try this out. So we can write max uv, and lean will helpfully tell us that the type max uv lives in type max uv plus 1. And we can also write concrete values for u of v here, and then lean will automatically simplify this, and we can actually like experiment with what these functions actually compute. So the maximum of 1 and 2 is 2 according to lean on universe levels. Okay. So however, under the hood, lean only knows about sort. So both type and prop are just syntactical sugar on top of sort. And so the actual typing rule that lean implements is stated in terms of sort. And here we hence need to invent a new function that does the maximum if the second argument is in type and returns 0 if the second argument is in prop. So if we look at this typing judgment here, we want to generalize both of the rules that we had before. In the one case, where we had functions between types that are in type, this v here is greater than 0, it's non-zero, because type u is sort u plus 1. And in the case for prop, the v here is 0 because prop is sort 0. And hence the resulting universe needs to be defined as follows. If v is 0, then this is the prop case, and it should return 0, which is prop. Or if v is non-zero, then it should return the maximum, which is the appropriate level for it in the type case. And this is indeed how this so-called Imax function is defined. So if the right argument is 0, then the result is 0, and if the right argument is non-zero, then it's the maximum. And we can just try this out again. We can do type of Imax u at 0, and lean will helpfully simplify this to type, which is type 0. So Imax u0 is 0 according to lean, and Imax u1 is the maximum. Once lean figures out that the right-hand side is non-zero, lean will simplify the Imax to max automatically. And this also works if we have v plus 1, and probably also if we write maximum of v plus 1, v plus 2, oh yes, this is easy, w plus 1, variables w, right. So in many cases, lean can actually simplify these expressions very nicely. So you can play around with this and see for yourself how this works. Okay, so this is the first difference. The way the universe level is chosen for the function type depends on whether the codomain is in prop or in type. The second difference is proof irrelevance. So recall that the ideology here is that there are exactly two propositions. There is false with no proof at all, and true with exactly one proof. Namely, well, let's check this here, print true. There is exactly one constructor, true to the intro. And with this in mind, that we want there to be exactly two propositions, we can implement a very nice principle called proof irrelevance that implements that implements in the Lean kernel itself that there is at most one proof of any given proposition. So stated as a formula, this means that for any proposition and any two proofs of this proposition, these proofs are equal. So we can prove this ourselves. And the important part here is that will come in very later in this lecture, in the section about subtypes, is that we can prove this by referral. This is true by reflexivity. Lean, you actually, in most cases, you do not never need to provide a proof that two proofs are equal. You can, Lean will automatically identify all of these proofs. If you have a proposition that depends on a proof, then Lean will unify it with any, will unify it with the same proposition where you replace the proof by another proof. So in most cases, you never need to care about what the actual proof is. Again, this will come in very handy when we work with subtypes later. And the motivation is, again, that both false and true have at most one proof, so this is a valid principle. And the third difference is a restriction on large elimination. So maybe let's first explain what large elimination is. Elimination refers to pattern matching. And large elimination refers to pattern matching on a proof, on something small, to produce data, something in type, which we call large. So an example of large elimination would be the following function, which, let's say, it takes a proof that there exists a natural number which is equal to itself and returns a natural number. So, and let's say we wanted to define such a function by pattern matching the proof and returning the natural number that was used to prove the existential statement. Okay. So now Lean immediately complains. It tells us that the recursor, so which is another name for the eliminator or the constant that is used to implement the pattern matching, can only eliminate into prop. Okay, so apparently this doesn't work. Why doesn't this work? Recall that Lean has proof irrelevance, so that there is at most one proof for every proposition. So all of those proofs that we could put in here, all of those proofs of exists n equals n are equal. However, if we could pattern match on the proof and return the natural number that is in there, then we would expect to the following to hold true, that foo applied to the exists introduction returns the same witness. However, if all of those are equal, foo would have to return, foo would need to be the constant function. So we can't have this. We cannot extract different data from a proof. We cannot. So the issue here is that we have many natural numbers, but there is at most one proof here. Hence, if we would pattern match it, we cannot return a different value for each of the proofs that are all equal. So note that this restriction does not hold for essentially, it only holds for existentials. It does not hold for other propositions, for other inductive types in prop, such as conjunctions. So if we have proof of, let's take two propositions P and Q. Then we can pattern match on this. Without any problem. That's because Lean knows that there is, because we do not learn anything about by pattern matching and introduction. There are multiple ways to construct an existential statement. If we would be able to reverse this, we could define a non-constant function on the proofs of this proposition. So there is at most one proof here. And if you would be able to define a non-constant function, this would be a contradiction. But here, there is at most one way to prove a conjunction. Hence, it is fine to pattern match on it, even if we construct a natural number. So in the demo file, we have here a more elaborate example. So which defines a function unsquare that, given an integer I that is square, which means that there exists a j such that I is j times j, then tries to return the j used to prove this. And then we have exactly the same contradiction here on a more real